Thank you. So the title of my talk is Riding Waves of Light to Discovery, and pretty much everyone should have heard about this crazy thing called wave-particle duality that light is. My guess is probably about maybe 100 people on the face of the Earth actually understand all the nuances of that. I am not one of them. But I do really enjoy waves, light and other kind of waves. But waves are really cool, and I thought I would share how they help us in astronomy discover things, how they might affect you in your everyday lives. Unfortunately, I should probably talk a little bit about how light is a particle first because of, I don't know, history. So the Greeks were very scientifically literate, and they had some very interesting theories about how light worked. They thought that light was little messengers that would come out of your eyes and go out and bounce off things and come back to your eyes and report on what they had found. There's one slight problem with that. Why can't we see in the dark? But they thought more about it, and there were plenty of very smart people, including Euclid, who figured out that light moves in straight lines, and he used that to study reflection. Ptolemy, who studied refraction, how light can be bent when it encounters new objects. And then this guy called Lucretius, who thought that light and heat are actually particles produced by hot objects. Unfortunately, no one really believed him, even though he probably had the most correct theory of the time. So there was lots of arguing, and I'm glossing over plenty of history here, until this guy came along, Isaac Newton, and said light is a particle. And everyone believed him because he's Isaac Newton, and he had some very smart theories about other things. Unfortunately, there were some mistakes in how he thought about particles being light, mainly that when they encountered more dense objects, they would go faster instead of slower. But it worked for most things. And in fact, it works for most things in our day-to-day lives, including just light and shadow. You can explain that perfectly well with light being a particle being blocked by objects. And if any of you were on the other side of the globe this afternoon and caught a supersonic jet home, you may have caught a very awesome example of this, which is a lunar eclipse where the Earth blocks the light from the sun hitting the moon. And this can all be explained by light being a particle, just light coming out of the sun, hitting the Earth, and not continuing. But also, scientists can use this theory of light to, for example, send solar sails out into the universe. And there's actually also another very timely mission going on, not just the 50th anniversary of Apollo, but the planetary has a CubeSat out, which is right here. Right now, it launched a couple of weeks ago, and it's called LightSail 2. And this is the first CubeSat demonstration of solar sailing. So how this works is particles of light come in, they hit your sail just like the wind, they bounce off and give you some momentum. And all of that can be perfectly well explained by light being a particle. Also, you should search LightSail 2 mission control. The Planetary Society is live streaming the telemetry from this CubeSat, and when they actually deploy this shield, it should be visible from the ground, so you can see where it is over the Earth and what it's doing. Also, the Breakthrough Initiatives is planning to send out solar sails, powering it instead of by the sun with a giant laser beam. But we can't explain everything with light being a particle, and the reason why I'm up here is because it's not exactly a particle, and waves are awesome. So these two guys, Robert Hooke and Christian Huygens, who you might recognize from other things, Huygens did a lot of astronomy as well, figured out that there's some things that can't really be explained by just light being a particle. So they proposed a theory that light was waves moving perpendicular to the direction of the wave propagating. And then along came Maxwell, and he wrote some equations for how electricity and magnetism work, and he figured out that electromagnetic waves travel at the speed of light. And he was like, well, maybe they're the same thing. Light is really cool, and because of it being a wave, it does some very interesting things. So first, we should talk a little bit about waves. So these two green and blue waves are interacting, and when waves interact, they don't just bounce off of each other like particles do. They actually interfere. And so when the two blue and green waves are in phase, meaning the peaks line up with the peaks, the troughs line up with the troughs, the resulting wave, which is the red one, adds together. And when they are exactly out of phase, meaning the peaks line up with the troughs, everything cancels out and you get nothing. And so this is a really cool property of waves and can pretty much explain all of the weirdness that I'm about to talk about. And one way that you can encounter this in your everyday life is in your car. If you're just driving down the road and you're listening to the radio, you can't be listening to Spotify or anything, you have to be listening to the radio, and you come up to a stoplight, and sometimes at certain stoplights, when you come up and stop, your radio will just go to static. And as soon as you start going ahead again, it'll be perfectly fine. And actually what is happening is different beams of radio waves are coming from the antenna. Some of them are coming directly to your radio in your car, and some of them are bouncing off of nearby buildings or other objects and take a little bit longer to get to your radio. And what happens is instead of all the waves arriving at the same time, some of them arrive a little bit out of phase. And that spot that you encountered was a dead spot where all the waves cancel out. And you can just scoot a little bit forward if you want to keep listening to your radio, and everything should come back. And all of this can be explained by just waves interacting with other waves. But going back to the history, how did they figure this out? And the way that they did this was with a slit experiment. So Thomas Young was the first person to figure this out, that when you shine a light on a very small slit that is approximately on the scale of the wavelength of light, instead of just having one beam of light that comes through, which you would expect if light were a particle, you get this thing called a diffraction pattern, which you can see right here. So not only is there a bright spot directly in line with the slit, there's also some bright spots away from the slit. And again, this can all be explained by just light having the same path length towards that middle spot and adding up, and light having a slightly different path length to this dark spot and canceling out. And you can actually do a very similar experiment to this at home with your everyday laser pointer. This would probably work. And if you have a metal ruler, if you shine it at a very shallow angle on the rules on your metal ruler, it has to be reflective, you'll see this little diffraction pattern. And this is called Shallow's ruler. And you can use this to measure the wavelength of the laser that you're using. Another really cool little example of this diffraction, the fact that light is a wave, is spots. So everyone knows when you draw a star, you draw it with some points. But points don't really make sense for what stars are. They're big balls of gas and dust. They should be dots, and they're very far away. So what you're actually seeing is some diffraction. So I want everyone, hopefully this will work, I want everyone to look at this spot and cover up one of your eyes or close it, and just relax your eye and watch as it gets really small. You should see not just a point of light, but some little things coming out of there. And it should look something like this. You can uncover your eye for that. Hopefully people saw something like that. And what that is actually little imperfections in the lens of your eye that are caused by the fibers coming together and joining when the lens formed as a baby. And when you take that as your slit, if you will, and see what the diffraction pattern is, you get this little spiky thing. You'll see this thing called the Fourier transform. I'm not going to talk at all about that, even though it's one of my favorite things. Come ask me afterwards. That's how you get from this pattern to this pattern. It's really cool. So how does this apply to astronomy? Well, telescopes are like slits. And most of the time, they're not perfect slits. So this is an example of what the Hubble Space Telescope primary mirror looks like if you were to just look down the barrel. So you got this, all the white is where the reflective bits are, and then you have a central obstruction where the secondary mirror is, and then you have little spider arms that hold it, and then these circles are pads where they used to pick up the mirror when they were installing it. And what happens when you shine light at this is you get something like this, a much more complicated but very similar diffraction pattern. And most people, when they look at this, they're like, oh, that's so ugly. There's just like all this blobs, and what's a star there and what's not. And this, to me, is one of the most beautiful things. You can see there's a star here. There's this secondary ring. You can see all the diffraction patterns. These spikes along the 45-degree angles are caused by these rings here, or the support structures. And this is actually what I do for my research, is I look at images like this, or my code looks at images like this, and taking into account how light interacts with the telescope, if it were a wave, tries to figure out whether this thing is just one star, or maybe there's something else there. And even if this thing were much tighter in or even fainter, we would be able to detect it just by analyzing all of these little blobs around that star as if it were a diffraction pattern, because it is a diffraction pattern. Most people would just treat this as noise, subtract it off, and try and find something. But if that secondary companion there is too close, it doesn't work. So I use this to try and look for binary stars, or actually binary brown dwarfs, so very low mass stars, to try and figure out how they form. And all of this, again, just different lengths of path that the light took to get to our detector from here to there, and how it encounters different parts of the telescope. So we heard a little bit, or a lot, about radio interferometers in the first talk. And again, this is exactly the same principle. Waves of light coming into your telescope, except this time, instead of one telescope, one slit, you have 50 or 60 different slits of each of these telescopes. And the reason why this is quote-unquote easy in the radio frequency is because the receivers can actually measure the phase of that light coming in. They can actually see it as a wave. And so when they record the light that comes into each telescope, they can just save all of that information, feed it into a supercomputer, and line up those waves to make an image. And I have some very pretty images of planet-forming disks, which we had a talk about a couple of months ago. But unfortunately, if you want to get higher resolution, you can go to shorter wavelengths. Unfortunately, as you get to shorter wavelengths, light tends to act more like a particle. It's still a wave when it goes through your telescope, but our detectors can't measure all of that information. And that is because of this guy, Einstein. And he did an experiment, which he actually won the Nobel Prize for, not relativity, It was actually for the photoelectric effect. So this is an experiment he used to show that light is not a particle, not a wave, but both. And the way this works is that you shine light on a metal or some other material, and no matter how intense that light is, no matter how many particles of light are hitting the piece of metal, if those individual particles aren't high enough energy, you're not going to kick off any electrons. So you tune that energy, and then the electrons start coming off. And so that shows that not only does the wavelength of light matter, but when the wavelength is too long, when your particles aren't high enough energy, no matter how many particles you throw at it, you're not going to get any electrons. And we use this all the time for solar cells. And in astronomy, we use this in cameras. So light comes in through our telescope and we want to record it. The way we do that is with a CCD, a charge-coupled device. And the photons interact with the silicon on the detector, and they free an electron, just like the photoelectric effect predicts. And that electron sticks around until we read it out, and that is evidence that a photon hit our detector. The downside is all the information you have is a photon hit your detector. You don't know what the phase of that light was when it hit your detector. So if you want to do interferometry, if you want to combine the light from many telescopes to get really high resolution images, you have to actually physically combine the light. You can't just save the data and combine it after the fact. So these are two probably the most popular interferometers right now. The CHARA array, the Center for High Angular Resolution Astronomy in California, and the Very Large Telescope Interferometer, very handily named there, as astronomers love to do. And what they do is they take light from each of these telescopes and they actually pass it down pipes to this central room. And in the VLT, they go underground into this long room here. And as I said, because our detectors detect light as a particle, we have to mess with it while it's still a wave. And so inside of this very long room, and inside this kind of shed-looking thing here, is what's called a beam combining lab, where we actually take the light from the telescopes and figure out what the different path lengths to all the different telescopes are. So this one's a little bit closer, so it's going to need a longer delay than the one from here, so that when we do combine it on the camera, all the light is coming in at the same time, in phase, together, so that we can actually make an image after some processing. But so we can actually make an image as if it were a telescope this big. So these carts move along really long tracks as you're observing to adjust for the different lengths to each of the telescopes as they point at different things in the sky. And with these optical or near-infrared interferometers, we can get some really high resolution images. So we can actually start to resolve the disk of a star. So this is a big red giant, maybe it's a supergiant, I'm not sure. And we're actually seeing that this is a circle, not a dot, with this very large telescope or array of telescopes. And if we watch it long enough, this is a really cool image where they saw that a disk of dust around a companion passed in front of the star. And we can actually watch that in real time in actually resolved imaging. We don't just see the star go fainter and then come back. We can actually see where this dust is and what shape it is. Another example is looking at how large stars spin and what their temperatures are on the surface. So you can see this very kind of oval looking thing is spinning so fast that the equator is actually bulging out, and it's a little bit cooler. You can see it's more orange than white here. And you can see some other spots on these stars where we can actually resolve the surface of these stars with interferometry. And another really cool thing we can do, I saw this animation in your talk, was actually watch two binary stars orbit each other. Normally when we see binary stars, they take tens to hundreds of years to spin around each other. And with this high angular resolution telescope, we can see them when they're much closer together. And in this case, it has a 13-day period. And these stars are actually interacting with each other. You can see some streams going in between there. And we just could not do this with a single telescope. There's no way we could build something that big. So instead, we take the light and we combine it. So hopefully I've convinced you that light being a wave is really cool. And it's not just a wave, it's also a particle, but waves are cooler. Thank you. And I will take some questions.
All right, thank you, Sam. We have time for a few questions. Oh, up there in the balcony.
So the question is, I think what you're getting at is why the detector interacts with light as if it were a particle and not a wave. And the reason is that the scale on which the light is vibrating at those wavelengths is just so small that we can't actually resolve it with, say, an antenna like you would with a radio receiver. And instead, we just see that a photon hit the detector and excited an electron. So yeah, at longer wavelengths, we tend to receive light as if it were a wave, and at shorter wavelengths, we tend to receive light as if it were a particle. Though even on both extremes, you can still demonstrate that it's both, which is really weird, but cool.
So cool. Any other questions? All right, well, with that, let's thank our speaker one more time. Oh, there's a question I missed. Oh, I missed it. I'm sorry. Oh, up there. There we go, way up high. Sorry.
Yeah. Is this the one you're talking about? Yeah, so the question was, when you look at this picture, you see all these kind of stripes that are from the support structures, other way, the support structures from the centromere. And the question was, could you offset the target to avoid some of that structure? And the answer is no. No matter where you put the star on your detector, you're still going to see these diffraction spikes because that light has already gone through your telescope. It doesn't matter where on the detector it is. All of the light that hits your telescope is going to interfere with those support structures. You can get rid of these diffraction spikes with a different telescope design. So the GMT, which I'm sure you've all heard about if you've come to Astronomy on Tap talk, the Giant Magellan Telescope, which is one of these 30-meter class telescopes that's going to be built in the next 5-ish years, hopefully. They have a very different designed mirror system that avoids a lot of the diffraction spikes that you would get with this, with the Hubble. Also, the successor to the James Webb Telescope, which hasn't been selected yet. They're still selecting down, but one of them is called LUVOIR, the large UV optical infrared something or other telescope. There are two designs for that. One of them is cheap and one of them is expensive. The cheap one has these support structures in the way, and the expensive one does not. It's an off-axis detector, so all of the light that hits the mirror and goes into the detector never sees any of these support structures. And that's really good if you're trying to do high-resolution imaging of, say, exoplanets, and you want to avoid these diffraction features. You're still going to get the rings, because that's just a feature of the fact that your telescope has an edge, but you're not going to get these long cross-like features.
All right, one more real quick question. How about right here?
There's a couple more. Yes, so you definitely, the question was, do you need to, and how do you control the angle of the solar sail? So the LightSail 2 mission that is demonstrating this technology definitely needs to control the angle. So what they're doing is they're up in this high orbit where the remnants of the Earth's atmosphere are not going to really affect the orbit at all. And they're trying to show that they can raise their orbit just using the solar light pressure. So what they're going to do is when they're moving away from the sun, they're going to expose that solar sail to get a little bit of velocity boost. And then when they're moving towards the sun, they're going to turn it sideways and avoid any backwards pressure to slow it down. And by doing that, oscillating, getting a velocity boost, and then not getting a drag, they should be able to boost their orbit up and show that this actually works. If you weren't in orbit, if you're just trying to go somewhere, it would be more like a sailboat where you can tack upwind or just sail downwind.
All right, let's thank our speaker one more time.